Those gradients are really effective.
Yeah. Sorry. Thanks, Molly, for not keeping silent this information. Am I audible now? I think so. Yeah. Okay, so that's the strategy. Yes, so it's perceived silently. That's a nuance there to be said. Okay, let's go to the gradients. So, okay, why do we use gradients? Who's familiar here with the Larmor or precession frequency? Who has heard that word? Or has not heard that word? Okay. I'll talk to you later then, and then let's talk first. That's fine. But in general, when we put a person in the scanner, right, and we excite it with our transmit coil, we get a signal, and that's oscillating at one frequency usually. And that's useless because there's no information on the location. That's why we use gradient coils. We modify the magnetic field in 3 directions in order to be able to tell where a signal is coming from. So this frequency, we modulate the frequency, the precession of the hydrogen nuclei in space. We use gradient coils for that. So that's why we use the gradient coils. There are 3. So usually, there's the main magnetic field in red. We have some shim. Don't worry about that. And we have gradient coils in 3 directions. And this is for a whole body system. So what it does, it applies changes to this main magnetic field in space in 3 directions. And therefore, the main magnetic field will depend on location. And therefore, the precession frequency will depend on location. And that will result in a very complicated oscillating signal. But using very famous mathematical tricks, we can reconstruct that to an image. So that's the game a little bit. So gradient coils are used for spatial encoding. So in 3 directions, we vary the Z components of the main magnetic field. Not talking about other complicated nuance effects of fields here. What we do in space, we vary the fields, okay? And that's needed to create images. Here you can see that. So here I have made an image. Oh, it's very fast. So modifying two gradients here, so we're looking at a 2D image, we can make a unique frequency for every location, okay? That allows us to do spatial encoding. When you do that during the signal generation or capturing the signal, we vary the gradients, we acquire these so-called echoes. And the spatial information is in this echo, in the oscillation, all these frequencies are in this. Okay, and the time it takes to take an image, that depends on how fast you can play out these gradients, right? So if you want to go faster, you have to shorten your readouts, okay? You can either do that by, well, accelerating technique like send, you skip lines, and you have to fill k-space, and you have to fill the image. You can just skip some lines and fill that with information of your receive coils. That's called parallel imaging. It's one branch of speeding up. Another branch to generate these signals faster by having faster gradients, a stronger gradient. So in red, you see that. If you have a faster gradient, you can go. Your readout range becomes shorter with a lot of benefits. Okay, so what? A little bit of the lingo in gradients for the gradient geeks. Spatial encoding we do. Encoding speed depends on the amplitude and the slew rate. So how do we? This is the amplitude. If you have a typical readout, certain echo time, this is where you collect the data. Right? This is where you rephase data, the signal. Here's where the echo is. Amplitude. And a certain slew rate. You cannot immediately hit the maximum gradient amplitude. It takes some time. That's the so-called slew rate. And the area you then make determines your spatial resolution. So if you want to zoom in, looking at smaller things, you also need higher gradients, right? You have to make this area. Of course, you can scan very long, right? Just very weak gradients, you can scan forever. But then we all know TT star decay, there's no signal left. Just that all these kind of factors will limit the game you can play. And that will affect fMRI, diffusion, perfusion MRI that do what's it called EPI readouts. Here's your typical EPI readout train. Your signal, like when a tuning fork, right? It also has one frequency, but it will decay out. The signal will be lost at some point. A lot of noise. And also this decaying signal will cause distortions, signal loss. And if you could then shorten all that, this will be mitigated. You will gain signal, less distortion. Okay, so this is a little bit about the intro on what gradients do, why you would do it, what effects it has on certain scans. Much more to be said about, but a lot of topics covered here. Phase velocity encoding, the Venks we talk about all use gradients also to manipulate the contrast mechanism. And we'll talk about this here only on the readout part. So why not just crank up the voltages and the currents through these coils we have? Very easy. Oh no, there are some limitations. First of all, the gradient amplifier has a max. These beasts, they go very hot and it needs to be water cooled. Can only deliver a certain amount of current and voltage. And also the coil itself, it has certain properties. The larger the coil, the larger the resistance, and the slower it acts. The slowness of the coil is called inductance, self-inductance. It's the property of a conductor to resist any change in the current. It's Lenz's law. It's just physics, but this is how it is. And the lower this value, the more responsive a coil becomes. And how do you do that? One way is to reduce the amount of windings or to make it smaller. So physical effects that limits our just boosting our gradients is peripheral nerve stimulation. You might have encountered this. Diffusion scans are notoriously affected by this. So biology will also limit our ways of boosting the gradients. What is peripheral nerve stimulation? Well, when you switch gradients, you'll see large swings in the magnetic field, right? And of course, in the middle, the swings are not so large. And basically, we're interested for the encoding is the slope. But at your feet, you'll see large absolute swings in the magnetic field, also at the head. And these will polarize the nerves and cause peripheral nerve stimulation. Another problem is the switching will cause sound. There we go. Works. We hit 1,000 hertz, we almost hit 50,000 hertz, and then maybe some hurt 18,000, 20 kilohertz. If you're a dog, I don't see any here, but you'll go a little bit further. And also babies. For babies, you also have to be careful with 20K oscillations. Let's keep going. So now we go to this work we've been doing. One way to mitigate, so we cannot make more power from the amplifier. We have to do something on the design to be able to go faster and stronger gradients. What we do is we make smaller coils, okay? That means you can generate more fields per ampere. Generally, they're more efficient. So for the same amount of current put through, we get more field, range field. They're more responsive, lower induction, and they have much higher threshold in PNS, because if you have a compact coil here, is the insert, the swings are much in the magnetic field are much smaller, right? That's kind of the trick we exploit for insert gradients. The disadvantage, of course, is this smaller coil, smaller field of view, not all anatomies fit, and sometimes you have to modify your whole system in order to be able to do this. So our friends in Zurich, they did a nice leg extremity coil. As Boosman, the GE has also a very interesting insert, very heavy. It takes almost a weekend to hold it in the system. So that's not so practical always, but it will really yield very nice results. Also, gradients now these days are very popular, for instance, for the new generation of MRI scanners. This just got published, I think, last month, 2 months almost ago already. Maybe you've seen it in Nature Methods, our friends from the Feinberg group. So they also have a very high gradient system in the 7T. And indeed, you see when you can have more performance, your echo times become shorter, you gain signal, you can go higher resolution, all super nice. And this is what they come up with. Here and now we're not that far yet. We've been working on it for several years, but this inspires us to keep going because it is a very interesting avenue to pursue. So this is now talk about our effort. We want to make a plug and play insert, so not they take a weekend to get in there. So minimal modifications, lightweight, fast install, deinstall, but high performance grading system. And at the beginning we thought about functional MRI. I give all the credit to Edwin Versteeg here, and now postdoc in our group. He just got his PhD last year, cum laude on this. So he had the true boots on the ground. Almost all credits should go to him in making it all work. And finally, after some years, we have some output going on this topic. So that's good. So how does it look like, this coil? Single axis coil, so not 3 directions. I mentioned earlier, it needs X, Y, and Z coils. We focused on the Z. Why? It's the most easiest design, just rings. So therefore, it's very high responsive, low inductance, can go very fast, and it's lightweight. 45 kilos. Yeah, I can carry it with 2 persons easily. It has a built-in RF coil, and these are the performances for this amplifier. So compare it to the standard whole grain system, so about 5 times higher strength and faster fluids. It can be water cooled. This is how we like to work. Simple, nothing expensive. You can make it too simple. So just a toy bath and some enthusiastic students. We can do a lot here. And installation time is about 15 minutes to get it in fast nowadays. Yeah. So we have to test PNS. Is it really? So how does it affect? You have to do this according to the guidelines. We did that, and we see at the PNS we can really drive it at short rise times and high strengths. This is where you cannot operate. So in red is a hardware limit. This is what it could do. And this is where you can operate. And you'll see in these Feinberg scanners as well that they will report on the hardware limits, but not necessarily where they're driving it at. So it's good to keep it in mind when you're just looking at the values and the specs we report. Then this is where you want to look at in the blue line. Very mild PNS. Why? Yeah, because it's focused on the head. It doesn't reach the large nerves. So with this system, we were able to, we can shorten the readout in EPI factor 2.5 almost. You can gain signal. Those not the most prettiest images, which is not due to the gradient core, but more due to the RF we had to really quickly build. We now have much better results there already, but you see that the echo time only, you reduce it, brings back a lot of signal. And so the moment you hit the reach, higher slew rates will not give you a lot of gains. Okay, now let's go to the sound. I mentioned that, so we have a very responsive coil. Let's drive it very fast. So not at this 1000 hertz for typical EPI, but 20 kilohertz. Okay, so how do you do that? Normal amplifiers do not do this. So we involved an audio amplifier. I like rock concerts and techno and all that. So that's what they use. And we had a student who was doing these kind of parties, and he pointed us to these kind of amplifiers. Very useful, quite cheap, but very powerful. And of course, with these high switching rates, you induce very high voltages. So we used an old trick from the 70s, EPI book by Turner et al. And amongst others. You can make a resonant gradient. So back in the day, amplifiers could not switch plus and minus very quickly. They had to do an oscillation, and they make resonant circuits. How do you do that? You add a capacitor bank. Basically, what you do, the gradient coil becomes like a swing. It has a natural frequency of the length instead of a fixed thing. And if you push it at the right moment at 20 kilohertz, it will be much easier to put energy in there. It's very simply said, but that's basically how it works. So you add a capacitor bank, you drive it with the amplifier. With the host PC, we send a trigger, and it will send out this 20 kilohertz signal to this gradient. Okay, now this is how it looks like. super fast. So this is the milliseconds. Yeah? So imagine usually these blocks are like this. This is when we're reading out these signals. Maximum we reach about 40 millitesla per meter. So not super high amplitude here, but very fast. It's amazingly high slew rate. It's about 26 times faster than the whole body. Also, at these frequencies, we had to test the PNS. All fine. This is about the limit. We can find mild PNS. So this is still within the operating range. You have Philips, you can, because you get this message, right? Are you in the safety 1 or 2 level? This is all good. Also, it checks tissue heating. It could be at these frequencies, you can do some heating. Also all within normal levels, nothing crazy. Okay, but now our imaging sequence will look a little bit different. This is how we normally scan, right? K line by K line by K line, and you skip a few if you want to accelerate with sense, okay? This is how we do it now. We reduce everything else, so in order to also mitigate the sounds. This is how we acquire data. It's in lanes, because this oscillating is the 20 kilohertz, so it's a kind of different way. So we cover actually more K space in one shot. So it's a segmented readout. With larger K space of the speed per TR and sound reduction without compromising scan time. The application we wanted to do was MP-range imaging, T1 anatomies, usually it's quite a loud sequence as well. You will hear. I will show you sound. It's not as loud as EPR diffusion, but you hear it. Everybody who was asleep, hopefully. But this is the typical sound. The aim was to at least reduce the sound, match contrast, assess image quality, quantitative, qualitative with a few radiologists, and also subject content. Okay, I'll show you. These are the images we obtained. This is already 2 years ago, so we are further already. But this is from that publication on this. I'll show here. I'll let you hear it again. Okay, and that is how it sounds. We even had to boost this sound a few dBs. So we're really getting into the ambient noise, and we can even hear the cryostate pump these days. So this is a bit the gain we have. I'll stop it. Yeah.
I think we got it. We understand.
Yeah. Now it's playing automatically. Yeah. So we have 2 radiologists assess the data, and they say it's at this stage, at that stage, quality was good enough for diagnostic value. But except for the temporal lobe, that's notoriously a problem with RF coils, transmit coils at 7T. Yeah, I'll say something about this later on. Also acceleration, and we can speed up things. So what you can do if you can skip scale lines, and you can also do that for the readout lanes. You can just separate them, and you can speed up things. So what's the effect? Normally, if you skip lines, you'll see aliasing, right? See it folding. You have to unfold the artifacts or the signal you don't want, and you get you have so less signal left, few K lines, that also your SNR is dropping drastically. But this is normal accelerating scans using sense or kind of, yeah. This is what we do with the ultrasonic readouts. So we can reach quite high, much higher acceleration factors without introducing too many artifacts. I'll show you the comparison later. But this is the effect. So we have some overlap between the lanes, and we slowly move them apart depending on the acceleration. Here you can see that, so it's normal sense. And of course, the amplitude is a dependency. So if you drive it at 40 millitesla per meter, you can look at good data at acceleration of 10 compared to sense. It's completely unusable. And here you see that same effect in terms of the G factor. That's a measure of the noise amplification for a acceleration technique. So the higher the color, the better it is. We see that at high accelerations, we are really at low G factor, to say around 1 here. So that's good news. I'll skip this. Yeah, I want to wrap up a little bit to the clinical part. What's next is that we're translating this to 3T. It was all because is it a toy for physicists? Yes, of course it is. But luckily we have partners and people interested in taking the next step out of our hands, pushing it to a product or going to the clinical field strength of 3T. This is one made by Tesla DC, our partner, commercial partner, industry partner. For this, I have nothing to declare financially or anything like that. So that's our 3T thing. The next thing is also to look at the other workhorse scans, flare, SWI, next to the T1. So we want to go for a fast, quiet protocol for the clinic. We're also working on quantitative MRI with the MR stat group here. It's a computational MRI group that can in one scan infer all kinds of contrasts. I'm also interested in looking at silent preparation modules. So I know PCASL is usually, at least in our institutes, you can kind of hear it. Also the vessel wall scans we use, quite noisy. So maybe these ultrasonic readouts can be of interest there or find some use. And of course, you can go to more axes. So this was all single axis, and the Z coil. You can go to double axis. And the problems will grow exponentially, but also more fun, of course, and more challenges to fix, which I like. So we have a dual axis now. Other application diffusion MRI, so we need 3 axes. So what we do, not using an audio amplifier anymore, we modified our gradient amplifiers to also produce 20 kilohertz outputs. You need to increase the bandwidth to do a hybrid. So you can do slow. So a diffusion pulse is, in frequency terms, very low frequency. And then do a very ultrasonic silent readout. That's the idea. And we built a 3-axis coil. That's what I like to do most, design how the conductor should lay and all that stuff. And then with our partner, they figure out the mechanics and the housing and the cooling. But this is the design, and then boom, this is it. So it was like 2 weeks ago, we picked it up at Victura, like an hour drive. And yeah, I always close my eyes and do shit on photos, but this is the team, so all credit to them. And a dinosaur in MRI, Johan Overweg, knows a lot about gradients. That was at Victura, the rest of the team. And I like to do things myself, so I drove this thing home, my own car in a crate, trying to avoid speed bumps, but it worked. It's quite a heavy thing. And then we tested it, of course, using oscilloscopes. It is a lot of fun. What's next? I talked diffusion, spectroscopy. Alex is also involved. Metabolic information, fast FC scans. They very, very noisy. Can I do this? Yeah. That's not a nice sound. And so this is gone. That's nice. And your bandwidth in your chemical spectrum shit is increased because of this readout. High increase your bandwidth as well. Single axis. Okay, dual axis as well. And we do different patterns, like Lissajous patterns. What else? So of course, this was all head. For the clinic, really likes to have body. So with an OTP funded by our Dutch government here, we can go to body. We're building now a coil. Of course, you get the PNS thing again. So we do a segmented version, and that introduces non-linear gradient fields. And we work now on how to reconstruct data in this non-linear regime. It seems promising, so we continue. And also with Maastricht, we're looking at the auditory system. It's a no-brainer almost when you can go silent. It's Elia Comisano. And also neonates I'm interested in. So I'm talking to the sleep doctor here in Utrecht, Jeroen Dudink. He's looking at sleep in neonates. And yeah, so maybe there's an interesting application for that as well for our technology. I think I want to thank you for your attention, and this is the team and the partners involved.